Man has always been a builder. Yes, man has always been a builder, but his structures have endured only when the materials he used were able to resist the forces of nature. Most of those forces we have found it easy to comprehend. The wind, the sun, the rain, and the snow. So understanding them, we have built our shelters against them. Simply at first, then as we acquired new skills and imagination, with increasing comfort, grace, and beauty. And with each advance, we might say to ourselves, this is good. This is beautiful. And this is durable. But always as we built, we took one thing for granted: the earth beneath our feet, the solid earth in which our structures were anchored. But the earth cannot be taken for granted. For sometimes in unexpected places and without a moment's warning, our seemingly solid earth will heave and twist and strain, wrenching our homes in its violent spasm, filling our minds with helpless fear. Leaving behind its hideous desolation. Desolation we have seen so many times and in so many places. San Francisco, Seattle, Santa Barbara, Long Beach, Helena, Manila, Tokyo, Tehachapi, Arvin, Bakersfield, and countless others around the world. Where next? Where no? We can only guess. If this be our fearful threat, where then shall we find our answer? We found our answer in the earth itself. For while the earth may tremble and quake beneath our feet, it also yields the rich ore from which we take our iron. Out of the iron we make our steel. And out of the steel we create the strength to support our buildings. Yes, even against the shock of earthquakes. For while the earth's shock can play havoc with those buildings which are poorly designed or built of insubstantial materials, there have been many examples that structures built of steel or reinforced with steel have been able to withstand the shock of earthquake. One such example was the famous old ferry building of San Francisco. Framed with steel, this venerable landmark was one of the buildings to survive the earthquake of 1906. With but minor damage to the tower. In the Pacific Northwest, a convincing example was the Smith, which, with its steel construction, withstood the earthquake of 1949. In Long Beach, California, the beautiful Villa Riviera, constructed of steel, was a notable survivor of the earthquake of 1933. And in Arvin, California, the Arvin High School, with its modern steel-reinforced construction, suffered only minimum damage in the severe Tehachapi shocks of 1952. What a contrast to the Cummings Valley School, not far away, which, lacking such strength, was reduced to rubble by the very same earthquake. One does not like to think of children trapped in a collapsing schoolhouse. From such convincing evidence, we have the proof that steel is an important factor in the construction of earthquake-resistant buildings. But in order to understand why, we must know something about the nature of earthquakes themselves. To begin with, movements of some kind are going on in the Earth's crust somewhere all the time. Movements which, in their own way, are as restless as the changing tides of the sea. Many of these movements are so minor that we ourselves do not feel them. But we know they're going on because our sensitive recording instruments constantly tell us so. On the other hand, there are movements so strong and violent that we do feel them, and very sharply. Many of these movements have taken place along the Pacific coast, a region which, to many people, has become known as the earthquake belt of North America. Let it not be assumed, however, that earthquakes are confined to this so-called earthquake belt. Actually, earthquakes have occurred in every state. The strongest shocks of record in the United States occurred in 1811 and 1812 in Missouri. Another earthquake, originating in South Carolina in 1886, was felt 1,000 miles away. Earthquakes are no respecters of locality. They occur because of some slipping or rupturing within the earth, and this produces a fault. Sometimes these faults are even visible on the Earth's surface, such as the famous San Andreas Fault in California. It was the slipping along this fault which caused the San Francisco earthquake of 1906, and several later ones as well. Sometimes, too, an earthquake may cause cracks or fissures at the Earth's surface. At one location, the Tehachapi quake of 1952 created a crack nearly 6 feet wide and 6 feet deep, a surface indication of some rupturing deep below. And it is there that our story lies. The Earth, as we generally understand it, has 3 layers: the outer crust, the mantle, and the core. The outer crust upon which we live has an average depth of 20 to 30 miles. Beneath this crust is the mantle, extending to a depth of about 1,700 miles. And beyond the mantle lies the core, extending about 2,150 miles to the center of the Earth. Now, as already mentioned, we know that movements are taking place constantly in the Earth's crust and mantle. As the movements continue, stresses are built up until at some weak point, the Earth's crust is overstressed and a sudden shearing or slipping failure occurs. It is the sudden release of stress by the slip that produces the earthquake. From this subterranean rupture, vast amounts of energy are released, which radiate in all directions through the Earth's crust, mantle, and core. These radiations are called seismic waves. By studying these waves, we learn much about the origin and intensity of the earthquake shock. Such studies are made at seismological laboratories, located at strategic points throughout the world, where seismic waves, whenever they occur, are scientifically recorded on sensitive instruments known as seismographs. The various seismological laboratories, by pooling their information, can trace the origin of the shock and plot the degree of strain caused by the earthquake as well as its aftershocks. The seismograph is but one of many delicate instruments which tell of movements in the Earth's structure. One unique instrument, for instance, has been installed in a tunnel under the San Gabriel Mountains of Southern California. A device so designed as to measure long-term strains in the Earth's crust. As these strains accumulate, the resulting movements, too slight to be seen with the naked eye, can be measured and recorded. And it is hoped that such findings may make it possible someday actually to forecast when and where earthquakes will occur. Also, a special type of seismograph, so sensitive a breath can set it in motion, is used to measure the actual movement at the Earth's surface during an earthquake and its aftershocks. With data gathered in this and other ways, scientists are able to recreate the movement and behavior of earthquakes long past. For example, a mechanical device which simulates the ground motion of the Long Beach quake of 1933 is used to illustrate how buildings react under varying loads. In addition to studying earthquakes which have actually occurred, scientists also learn from purely hypothetical quakes. At one California university, itself a victim of the 1906 earthquake, a mechanical test creating shocks of varying degrees of intensity helps to determine how structures will react to possible future earthquakes. This study is all the more significant because the test structure is an actual scale model of an actual building located at Bush and Montgomery Streets in San Francisco, the Alexander Building, a slender 16-story structure built on a framework of steel. Like its laboratory model, the building itself is furthering earthquake research. For sensitive instruments to measure accelerations due to shock have been installed in the building at several different levels. With the aid of these instruments, it is possible to study the building's reaction to the forces created by earthquake movements whenever they occur. These, of course, are only a few examples of many types of research going forward all the time. And we have learned from such research that different types of buildings react in different ways to earthquake shocks. These differences can be illustrated by comparing the reactions of a low structure, a tall, slender structure, and an L-shaped structure. In the case of the low structure, when the Earth's movement causes the base to move, the roof, because of its inertia, tends to lag behind and does not immediately follow the ground. Its weight, therefore, creates considerable stress in the members connecting the floor to the roof. The resulting strains, known as shearing strains, may cause the structure to collapse, unless the members are properly braced and tied together. With a tall, slender structure experiencing the same ground movements, the building oscillates, causing various bends. Consequently, the frame must have sufficient flexibility to permit the structure to assume the distorted shapes. Without such resilience, the structure will suffer excessive damage. In the L-shaped structure, if the ground movement is parallel to one wing, this wing, because of its length, may have considerable resistance to the shock. But the other wing is broadside to the movement and consequently will deflect more. The unequal deflection between the two wings will cause a twisting action. And if the building is not properly braced and tied together, this twisting or torsion may cause failure at the junction of the two wings. Obviously, if buildings are to withstand these destructive forces, they must be constructed of suitable materials which will not fail. It is for this reason that steel and steel-reinforced materials have become the key to earthquake-resistant construction. For steel is tough. It has two qualities highly essential to earthquake resistance: strength and ductility. Ductility is the ability of a material to undergo distortion, that is, to absorb energy without breaking. Steel has this ability. An actual load test shows that a load of 5,000 pounds is well within the elastic limit of this particular beam. For when the pressure is removed, the beam immediately returns to its original form. Even when pushed beyond its elastic limit, steel can sustain great loads. In this particular test, a load as high as 68,000 pounds distorts the beam considerably, but in spite of this, the beam still holds. So steel has not only ductility, it also has strength. Strength which is measured by its ability to withstand tension, compression, and shear stresses. And it has the ability to impart strength to other materials. Concrete is a good example. Here, a transparent form makes it possible to see how steel reinforcing bars are placed to best impart their strength to a concrete beam. From this reinforcement, the beam will gain both shear strength and tension strength. This can be shown by making a comparative test of two concrete beams of exactly the same dimension. The first beam reinforced with steel, the second unreinforced. The pressure is applied equally on both beams. At a load of 5,000 pounds, the unreinforced concrete is shattered, while the steel reinforced beam has sustained only minor cracks. As the load increases, the damage becomes visible, but the beam will not give way. Even at 30,000 pounds, it will not give way, simply because of the strength of its reinforcing steel. Perhaps no one knows this better than a wrecking crew engaged in demolishing old buildings. If the walls are not reinforced, whether they be of brick, stone, concrete, or any other material, they can be brought down without much difficulty. But if those walls be reinforced with steel, the wreckers have a bigger job on their hands. It will take a tremendous amount of battering to even chip the walls away. And even then, the steel still holds. The only way it can be removed finally is with the chisel or cutting torch. Yes, steel has both strength and ductility. But even these qualities were not enough to save a steel elevated water tank in the Tehachapi earthquake. Its collapse came about because, although built of steel, it was not properly designed to resist earthquakes. As another example, a brand new high school in Helena, Montana, only 1 month old, collapsed in the earthquake of 1935. It was a partially steel reinforced building, but again, not designed to resist earthquakes. Otherwise, it might be standing today. There are many aspects of good design, but insofar as earthquake resistance is concerned, one fact is of prime importance. The various components of any building must be tied together in such a way as to provide structural continuity. Structural continuity would be entirely lacking, for instance, in a platform resting on 4 uprights but not fastened to them. Such a structure might support a sizable load, but only so long as the force of the load continued to be vertical. If the structure were subjected to a horizontal force, inasmuch as its parts are not tied together, it would simply topple. Suppose, however, that platform and uprights are fastened together and partially braced. Now the structure offers some resistance to horizontal movement, but not enough resistance to withstand twisting or torsion, so that, again, the structure will fail. It is only when all members are properly tied together on all sides that the structure achieves true continuity and the strength to resist movement from any and all directions. Perhaps a more homely illustration is the simple cardboard carton. With its lid open, the carton offers little resistance to outside pressures. But if the lid is closed and securely fastened, the carton has strength to resist forces from any direction. The lid forms what is known in structural design as a diaphragm, which, when properly tied in, gives strength to the whole. In much the same way, a building derives strength from its floors and roof, for these are the diaphragms of the building. But as in the case of the cardboard carton, these diaphragms must be tied in properly in order to provide a maximum of structural continuity. Here again is one of the advantages of steel, for in addition to its strength and ductility, steel is workable. It can be fashioned and fitted in countless ways, which not only facilitate construction, but make it possible to achieve complete structural continuity. Much of this is done before the steel even reaches the construction site, at the fabricating works, where steel is fabricated into convenient units. Units which, because they're properly engineered, will give a building the strength it needs to resist the forces of earthquake. Thanks to such modern techniques, intricate assemblies of every size and description can be fabricated and transported to the construction site, where erection time is saved because of the work already done at the shop. Base plates are fastened to their anchor bolts. Columns and girders are fitted into place. And as the building grows, each member is tied into other members, so that finally all units are integrated into one endless continuity. It is from this continuity and from the strength of its steel that the building derives the ability to resist even the shock of earthquake. And it is fortunate indeed that the strength, toughness, and ductility of steel can be given to many materials which otherwise might be weak or brittle. Concrete is only one example. With steel reinforcement, the beauty and utility of brick can be used in new and safer ways. Glass becomes stronger and safer. Plaster acquires form and durability. And masonry is given a dimension of strength and continuity which the material alone cannot provide. With the aid of steel nails, clips, and bolts, wooden structures acquire the same essential continuity. Even buildings with many openings and large areas of glass can withstand shock if they're properly designed and constructed. For each material has its purpose, and for all building materials there is one common denominator: steel. Nor have we seen the limits of what we can do. Public-spirited men everywhere are working constantly to advance our knowledge of earthquakes, of earthquake-resistant design and construction. Geologists, scientists, structural engineers, research engineers, architects, earthquake men, and building men. The knowledge they contribute is vital to our welfare, but that knowledge alone is not enough. It must be followed by public understanding and public action. So it is that public officials all over the country are re-examining their building codes and causing codes to be revised. Codes which will protect the people of their communities not only against fire, flood, and storm, but against the unpredictable threat of earthquake. Through sensible compliance with these codes, many communities have caused schools and other buildings to be abandoned solely because of unsafe design or construction. Many communities, realizing the danger in overhanging parapets and other gingerbread construction, have enacted legislation requiring them to be remedied or removed, and with good wisdom. For even if the building stands, its unsupported parapets and ornamentation are more than likely to be shaken down when the earthquake strikes. And beware to those below. In the city of Los Angeles, the building code requires that some types of parapets be removed and replaced with steel reinforced bond beams, which, when tied into the main structure, reduce hazards and often give additional strength to the building. Removal is not always required, however, for with certain types of parapets, it is possible to tie them into the structure with steel bracing, thus reducing the accident hazard. So we know what we must do. We must make our homes and our buildings safe. We must build them soundly to give them lasting strength. And those entrusted with public responsibility must see that proper codes are not only enacted, but also enforced. For while we cannot yet predict when or where the next earthquake will strike, we know that with wisdom, foresight, and continuing research, we can arm ourselves against it. We can use our weapon, steel. And when we use it wisely, even the earthquake will lose its terror. Our people will be safe and secure.